Welcome to Ask and Learn.
So now we have some damping in the problem. So we have this bar here that's pivoted about a point here, and we have a spring force and a damping force here. And I've drawn these so that they are opposing the motion. So the motion is positive this way, and this wants to pull it back, and this wants to push it back to be horizontal. Now we take moments about this point, and I just said, that's J sub B. I'm not sure why this is point B here, according to the book. And then we have the moment from the spring force, where this distance here is A, and then we have the moment from the damping, the damper, and then this moment arm is 2A. And then we have a static term here that's creating a moment from the gravity, and it is mg a over 2, just because we know the distance from the pivot to the center of mass here is a over 2. Now the spring force, again, I'm assuming angles are small here, so the spring force, the change of length, the displacement of this point is roughly a theta, if theta is small. And then we also knew that we had some static deflection or static deformation in the spring because of gravity here. So the total change in length in the spring is the amount from the rotation plus the amount that was caused from gravity. So this rotation theta is measured from the equilibrium position that's caused it already to rotate a little bit because of gravity. And then we have our spring force, or our damping force, is just C times the let's see here. Well, why do I have 2 here? What's the problem? Let's see here. Why did I have a 2 here? Oh, I know why we have 2 there, because this is proportional to the change in velocity, or the time differential of the change in length. So it's c times delta dot, and the change in length is roughly 2a theta. The change in from here to here, because the arm here is 2a, and so this distance here is roughly 2 theta. Taking a time derivative, we get 2 theta dot, multiply it by c, and we get an approximation for what force we have in the damper here. So we take moments about this point, and we can figure out that the mass moment of inertia of this bar, take by the center of mass and the parallel axis theorem, just gives us ma squared. And so we have from the spring, plugging this into here, we get this term and this term. And then from the damper, we get this term, and then from gravity, we get this term. But the static deflection is defined so that it cancels out the gravitational contributions. So this cancels with that, and that means that theta is measured from the equilibrium position, which in this case would be slightly rotated clockwise, because the center of mass is to the right of the pivot point. We can then cancel out a's everywhere and divide through by m, and this becomes our equation governing the motion. And the natural frequency is square root of k over m. And so we can see here that our equivalent stiffness, our equivalent damper, before I multiply through by m, our equivalent damper is 4c. And we're asked about keeping that below the critical value, which is 2 times the square root of mk. And so that says that c must be less than 1/2 square root of m times k. So as long as that is below below the critical value, as long as this is below this, then we have a system that is underdamped.